Hello and welcome to my talk on quantum relational Hoare logic with expectations. So in this talk, first I will say a few words about what relational Hoare logic is, then recap the quantum variant of relational Hoare logic. Then I will come to the main contribution of this talk, QRHL, quantum relational Hoare logic with expectations, and then say a few short words about one example that we analyzed in our logic, the quantum Zeno effect. So what is relational Hoare logic in general? Relational Hoare logic is a class of logics that are used to describe the relationship between two different programs. And essentially what this logic can tell us is how do the variables between two programs relate. So here I have given an example. Let's say we have that the variable x in the first program equals the variable x in the second program before execution. And the first program increases x by 1, the second program assigns x to y, and then we will have that x in the first program equals y in the second program plus 1. So this is an extremely simple statement, nothing very surprising happens, but it's an example of the kind of things that a relational Hoare logic allows us to express here in the deterministic case. And a relational Hoare logic can express much more complex relationships between programs, and it allows us to build up a judgment about the whole complex program from an analysis of all the individual building blocks. So in that respect, it's very similar to normal Hoare logic, which does it with a single program. So what are relational Hoare logics for? The most common and probably most well-known application of relational Hoare logic is in the analysis of security proofs of cryptographic protocols. So when we want to formally analyze a cryptographic protocol, we split the security proof in a so-called sequence of games. So we write the original situation that we analyze, then we write a slightly changed one, a slightly even more changed ones, and so on. And we need to analyze the relationship between those games in the sequence to make a security proof. And this can be done using using relational Hoare logic. More specifically, for analyzing cryptography, we need one variant, namely probabilistic relational Hoare logic, as used in the EasyCrypt tool. But we are not limited, the idea of relational Hoare logic is not limited to the probabilistic case. We can also analyze, for example, the quantum case, quantum relational Hoare logic, as done in the QRHL tool for doing quantum security proofs. So, since we will be looking at quantum relational Hoare logic, QRHL, with expectations, I should first explain what quantum relational Hoare logic is. So this is not the contribution of this work, but the foundation for it. So in quantum relational Hoare logic, different from normal relational Hoare logic, we look at programs that have quantum variables. So I denote them by fat x, bold x, and bold y. So an example judgment in quantum relational Hoare logic would be something like this. The precondition is x1 equals cat 0. So meaning in the beginning, the variable x in the first program is cat 0, and we don't say anything about the variable x in the second program. The first program applies the Hadamard matrix to x. The second program initializes x with cat plus. And then we say that after this, the variable x in the first program equals the variable x in the second program. Now, here are a few things that are important to understand in this example. So first, the programs here are written in some elementary while language that allows us to not only do classical operations, but also apply unitaries, for example, to quantum variables or initialize them. But more crucially, we need to understand what are the pre- and post conditions. So they are actually subspaces of the space of all quantum states. So when you look at the state of a quantum program before or after execution, this is described by a quantum state. So this state describes what the whole memory of the program is in. And the predicate is a subspace of the space of all possible configurations of the memory. So for example, if the memory could be something like cat 0, and the quantum state corresponding to the classical state 0, or it could be cat 1, so if our predicate wants to allow both these situations, then it would be actually the subspace spanned by cat 0 and cat 1, which is the space of everything. So in particular, if our predicate allows us to say that two certain memory states are possible, then any superpositions between these will also be possible. So this is the implication of using subspaces as predicates. So this is the most important thing we need to remember about quantum relational Hoare logic at this point, because this is the aspect where QHL with expectation will differ from it. So how do we actually define QHL? Because what I've shown you so far is just how can what is the vague intuition of QHL? What are the components of a judgment, the precondition, the true programs, the postcondition? However, interpreting a QHL judgment is not completely obvious, because we are talking about the relationship between the memories of two programs that are actually not running essentially in the same system. So a first attempt to say what such a judgment means would be to say for any initial quantum states that describe the initial memory of this program and of this program, so for any initial quantum states that satisfy this precondition, and then after applying those two programs to those two quantum states, we get the final quantum states, and the judgment, this whole judgment then would state that the final quantum states satisfy this postcondition. Now at the first glance, this seems to be the most natural way how one would express this. However, there's a problem, because it's not clear what it actually even means for two quantum states to satisfy a precondition or postcondition that is described as a subspace of all quantum states on two memories. Yeah? Remember, each initial quantum state is a quantum state describing the memory of one program, and now we ask, what does it mean that they together satisfy a predicate? One might naively assume that one just composes these two quantum states to a product, to become a product system, but that doesn't work out, because then those two quantum states would always be independent in the two systems, and something like x1 equals x2 would rarely be something that we can meaningfully hope for. Instead, I should have also said what satisfying a predicate exactly means. So given a quantum state that is described as a mixed state or density operator, satisfying a predicate, so being in the subspace, simply means that the quantum state is a probabilistic mixture of pure states that are all in this subspace described by the predicate. So, but how do we resolve the problem of saying what it means for two quantum states to satisfy one predicate? And this is done by this addition here. So instead of saying the two quantum states satisfy the predicate, we say for two initial quantum states with a coupling that satisfies this predicate, we want the rest to hold. So what is a coupling? A coupling of two quantum states is a joint system that has the two quantum states as marginals. So imagine, for example, that quantum system 1 would be in the state cat 0, quantum system 2 would be in the state cat 1, then a coupling would be a joint, one possible coupling would be the joint system in the state cat 0 tensor cat 1. However, when our quantum states are mixtures, the coupling is not unique, and there could be many possibilities, and a coupling is basically a possible, but not necessarily unique, view of how two quantum systems can be seen as parts of one big one. So our definition now becomes for initial quantum states with a coupling satisfying the Proust condition, after applying the two programs, we get final quantum states that also have another coupling satisfying the postcondition. And this is actually in spirit quite similar to what happens in the probabilistic setting, where we are not talking, we are talking of couplings of distributions. So the intuition is the same. However, we end up having a number of additional subtleties due to entanglement and so on, which I am not going into in this rough overview. Just as a side note, for one crucial thing is that the coupling should be separable, so no entanglement should be involved there. Okay, so this definition was already known before the present work, but there are some limitations that we encounter when our predicates are modeled as subspaces. So here are some examples of things that are not possible to express when predicates are subspaces. So for example, even if we're limiting ourselves to non-relational Hoare logic, so something where we express something about just a single program, we would not be able to state something like this, like if the variable x is in the state cat0 before we run the program, then the variable x is very close, up to an epsilon error, to cat1 after running the program. So an example of this might be if C is a program that applies a quantum bit flip, but only has an approximate implementation, maybe involving quantum error correction or something like this. And similarly, to give an example in the relation case, we would not be able to express something like if x1 equals x2 and we run the program, then x1 very closely equals x2. Again, if we would, for example, have to deal with error correction, we might encounter such a situation. So why is it not possible to express this? Well, if we look at this postcondition, for example, this says this does not say x equals cat0. It says x equals cat0, or it equals cat0 plus a little bit. Sorry, I said that. So this does not say x equals cat1, but it says x equals something very close to cat1. So if we want a predicate that expresses this, and this has to be a subspace, it would mean that it contains not only cat1 and cat1 plus a small error, it contains also the superposition of all quantum states that are close to cat1. Unfortunately, even if epsilon is extremely small, we still, the span of cat1 and a small disturbance of cat1 is already the full quantum state spanned by cat0 and cat1. So this means that such a precondition could only be expressed if we allow x to be any superposition of cat0 and cat1, but that gives us a trivial postcondition, because any quantum state is a superposition of cat0 and cat1. So it would not be possible to express this without ending up having a trivial postcondition that essentially just says true. And this problem is inherent to the subspace predicate approach. So we ask ourselves, can we write down predicates, or can we give a definition of predicates that allow us to get around this? This allow us to have quantitative statements that don't say x is cat1, but x is cat1 up to some error or something like this. And in fact, as in the non-relational case, so for normal quantum Hoare logic, such a solution to this problem is already well known for quite some time. And the idea, what we can do is to use, instead of predicates that just say yes or no, we use expectations. So what is an expectation? An expectation is, instead of using a subspace, we use an operator or a matrix. So we write the precondition by giving some matrix that operates on quantum states, and this matrix is supposed to tell us how much a given quantum state satisfies the predicate that we are looking at. So basically, an expectation assigns a certain number of points to any quantum state rho. So the actual formula is we take the trace of A times rho, but the exact formula does not matter very much for the understanding of this talk. So now, instead of having a predicate that just says this quantum state is satisfies me, or this quantum state doesn't satisfy me, instead we have an expectation that for one quantum state would say, oh, this state is very good, and for another state it would say, this state is not very good, it is almost zero. And in particular, we could look at an expectation that would say 1 point for the state cat1 and somewhat less for a state close to 1. And this would allow us to express something like the post-condition, the state after execution is close to cat1 by just writing the expectation that gives full point only for cat1 and a diminished point for something close to it. So, takeaway message, an expectation is a quantitative predicate. Now, how can we integrate expectations in quantum relational Hoare logic? So here's again an example judgment that we will look at. In the middle, nothing has changed. We have two programs. They don't have to be these, of course. But the pre and the post condition are given by operators or matrices that are applied to the quantum state. And because these operators do not have yes-no semantics anymore that tell us this state is okay, this state is not okay, our definition of QHL that I sketched cannot be used in the same form, because here it says, for initial quantum states with a coupling rho in it that satisfies this precondition, well, we can't write that, because satisfaction is quantitative. So we need to cross these lines out and come up with something else. And it's actually not too difficult to say what it is, because what we want is that how much the post condition is satisfied is at least as much as how much the precondition is satisfied. In that respect, the definition is very analogous to what we do when we are talking about non-relational quantum Hoare logic with expectations. So what we do is we require for any initial quantum states with some coupling rho in it, not necessarily satisfying any specific precondition, after applying these programs, the final quantum states have a coupling rho final such that the satisfaction of the precondition, so this is the quantitative amount, how much points our precondition gives to the initial state, is smaller equal to the satisfaction of the post-condition. So how much the operator B assigns to the final coupling rho final. And this definition, it's basically a direct combination of the definition of QHL and definitions that we have seen in non-relational quantum Hoare logic with expectations. However, there are some subtleties that need to be dealt with, so it's not all as obvious as it might seem at the first glance. One example of an issue that we run into is that this definition here, as I have sketched it so far, does not work well with non-terminating programs. And I'm not even talking about the case where we actually want to analyze the non-terminating behavior. Even if we have two programs that terminate with probability 1 on all states that are allowed by the precondition, but they may have non-terminating behavior on, for example, invalid inputs. Even then, this definition will actually behave quite badly. I do not want to go into the details in this talk for time reasons, just to say that there's extra work needed in defining what this means, and you can see this in the paper. Furthermore, our work has covered this expectation QHL definition not only for finite dimensional quantum states, so we allow infinite dimensional variables, which is important if we, for example, want to have programs that work with quantum ints or quantum lists where the length of the list is in superposition and so on. And finally, our work gives a number of reasoning rules for reasoning about expectation QHL, because just the definition alone, of course, does not allow us to conveniently work with this logic. So instead, for every statement in the simple while language, we have one or several reasoning rules for operating with programs that are on one side or with programs that work in lockstep between the left and the right side. So all of this you can see in the paper. I will not go into it at this point. So let me, to finish, just give one example of what we can express in QHL that we have also analyzed in the paper. It is the quantum Zeno effect. So consider the following situation. We have a quantum bit here described by a circle with a line whose angle describes the value of the qubit. And this qubit is in state ket 0 to begin with. So you can think of it as a horizontally polarized photon, for example. And then we apply a small rotation to it, and then again a small rotation and a small rotation. Here illustrated only 3 rotations, and then we have the state ket 1. But in general, you could have very, very small rotations and a lot of them, so that it becomes almost a smooth transition from ket 0 to ket 1. So this we can describe in our while language. I will not go into the syntax of what is written here, just that you get an impression. And then we can look at a separate experiment that does something else. So here we again start with a qubit in state ket 0, but instead of rotating it, we just measure whether it is in the place where we would have expected it to be after rotating. And then we do the same again. So we measure whether it is now rotated even further and even further. So we do not actually rotate the qubit, but we just measure whether it has rotated. Again, we can write this as a program in our language. And the curious thing about quantum mechanics is that if we do this in small enough steps, then just doing these measurements has the same effect as rotating the qubit. So the second program should do the same as the first program, at least in the limit if we make infinitely small rotations. But of course, we don't do infinitely many, we just do a large number. So if we would try to show that these two programs here, or these two programs, do the same thing in QHL without expectations, QHL would just say, no, they don't do the same thing, because QHL cannot deal with the effect that there is only a tiny difference between the two programs. But in expectation QHL, we can express the statement that these two programs do almost the same thing. So I've written here the final judgment down as an example to give an illustration. So we have the two programs left and right. These are the programs I showed you on the slide before. The post condition is the qubit y is the same in the two programs at the end. And then we have the precondition. So here we have the identity. So the identity is, when we are talking about expectations, the trivial precondition. But it is multiplied with the probability cosine pi over 2n to the power of 2n, where n is the number of steps in which we rotate. And the interpretation of this is that the post condition, the equality of the two qubits, holds with this probability. And this is a term, this is maybe not be immediately obvious, that for large n will converge to 1. So this says the left and the right program will do almost the same thing. Yeah. So we have now seen in our logic, and this is that the quantum Zeno effect indeed works and gives us the same effect whether we rotate and measure. And the whole example I showed you here can be derived inside our logic. So we do not need to use any meta reasoning about the quantum Zeno effect or anything like that. So to conclude, we have shown a logic for reasoning about pairs of quantum programs where we do quantitative reasoning because we have expectations. We have some open questions for future work. So for example, a so-called frame rule is something that we have not yet managed to construct, and tool support for reasoning on the computer would be something very valuable. And I would also like to mention similar independent work by Barth, Su, Yingyu, and Chu on Popple 2020, which does something very similar, but a number of design choices are different. See our paper for a comparison. And finally, I would also point out that there are open positions in this area. So if this topic fascinates you and you're looking for a PhD or postdoc, please contact us, and maybe we can work together on these things in the future. Thank you for your attention.